Hello Year 12s and welcome back to Mathematics. In today's lesson we're continuing with our topic of sequences and series, and we're going to be looking at geometric sequences or geometric progressions. Now last lesson we talked about arithmetic progressions, and what arithmetic progressions were they were sequences where each time you went up by a term you went up or down by that common difference. And so here we notice that the pattern for the pattern for an arithmetic progression was that Tn minus 1 is equal to the common difference. And we also worked with proving an arithmetic progression by taking our two consecutive terms and subtracting it and showing that's equal to the subtraction of another two consecutive terms. And we also found that the nth term in arithmetic progression was a plus n minus 1 times d. What we're talking about today is a geometric progression. Now, with a geometric progression, let's just have a look here. A geometric sequence or geometric progression is defined by the following. Instead of doing subtraction of two consecutive terms, we take two consecutive terms and divide it, and that's equal to r, where r is a constant and it's a common ratio. So here, instead of going up by the same number each time, we are actually multiplying to get to the next term by we're multiplying to get to the next term. So for example, if I start off with 1 and I had a geometric progression where I multiply by 2, that means that every time I go up, I go multiply the previous number by 2. So for example, 1 times 2 gives me 2, 2 times 2 gives me 4, 4 times 2 gives me 8, 16, and so on. This is an example of a geometric progression. Each time we go up, we are multiplying by that common ratio of r. So what we want to be able to do is, just like we did last lesson, we want to derive a formula for the nth term of our sequence. So here, like we did last time, the first term in our sequence, we call it a, and then when we want to get to our next term, we multiply by r. And so here, for my first t2, I'm just going to get a times r. So then for the next term, t3, I'm multiplying by r again. So t3 is just going to be t2 times r. So a times r squared. R squared, yes. My bad. The next one is t4, which is t3 times r, which is a times r to the power 3. Now, just like we did last time, if you have a look at my term and also the power of r, there's a bit of a pattern here. So here, the power of r is just one less than the term that we have. So the nth term of a geometric sequence is a r to the power n minus 1. Now, just like my arithmetic progression, which I mentioned at the end of the lesson, this is on your reference sheet. This is on your reference sheet, so you don't need to remember this formula for the nth term in a geometric progression. However, the following part, the proof for a geometric progression, we do need to remember. So this, just like we did with our arithmetic progression, when we did t3 minus t2 is equal to t2 minus t1, we're going to need t3, our third term, our second term, and our first term, but instead of doing minusing, we're going to be dividing. So here, if t3 divided by t2 is equal to t2 over t1, then we have a geometric progression. Okay, so let's actually go and solve a few problems for our geometric progressions. So the first one, find the values of x such that 3, x plus 4, x plus 10 form an arithmetic and a geometric progression sequence. So let's have a look at what happens when we've got an arithmetic progression. Now, if you remember, this is actually just to highlight the differences between the two. If my screen loads again, there we go. Just to highlight the difference between the two. Now, with a arithmetic progression, just remember, so AP, condition was that t3 minus t2 is equal to t2 minus t1. So let's just before we do that, any of this, I realize I should probably do this instead. Let's just figure out what our terms are for our progression. So for this progression, t3 is equal to x plus 10, t2 is equal to x plus 4, and t1 is equal to 3. Now, what I had written down was for an arithmetic progression, for a AP, the condition was that t3 minus t2 is equal to t2 minus t1. So if I want my sequence to be an arithmetic progression, it needs to follow this pattern. So let's just sub in our values here. Now, because we're dealing with, we're not dealing with numbers, we're actually dealing with some algebra, we can just sub it into this equation here. So T3 was x plus 10 minus T2, which is x plus 4. And that needs to equal to x plus 4 minus 3. Okay, let's just simplify both our sides. So on our left-hand side, we've got x plus 10 minus x plus 4. That just becomes 6 is equal to x plus 1. So therefore, x is equal to 5. So in order for this sequence to make an arithmetic progression, we need x to be equal to 5. However, for a geometric progression or geometric sequence, we need T3 over T2 is equal to T2 over T1. So that's where the differences are for our geometric progression. So here we can just sub in our values here. So x plus 10 over x plus 4 is equal to x plus 4 over 3. And so when we're solving this, we can just cross multiply. And so here I multiply the 3 over, I get 3x plus 10 is equal to x plus 4 squared. And I can just expand this and start to solve for x. So here on my left hand side, I get 3x plus 30. And on my right hand side, I get x squared plus 8x plus 16 using my perfect square expansion. Now I can start to solve this. This is a quadratic and I can just move all of my terms to one side. So I can move all my terms to the right hand side. So I get x squared plus 5x minus 14 is equal to 0. And so here I can factorize. I'm looking for two numbers that add to give me 5 and multiply to give me negative 14. And so here my two numbers are going to be x plus 7, x minus 2 is equal to 0. So therefore x is equal to negative 7 or 2. So here with a geometric progression and arithmetic progression, those are the two differences. An arithmetic progression, you're going up by that common difference. So each time you're going up by the common, each time you're going to the next term, you add that common difference. But with a geometric progression, you're multiplying by the common ratio. And so here you only divide consecutive terms. So that's how we can prove, this is a way that we would prove a geometric progression versus an arithmetic progression as well. So over the page, we have a few more examples of this. So let's have a look at this one. Find the first term A and the common ratio R of a GP where the fourth term is 30 and the sixth term is 480. Now we did a similar question to this, but with arithmetic progressions. So here what we need to use is the fact that the nth term in our geometric progression is ARn minus 1. Because here we are given the fourth term, which is 30, and the sixth term, which is 480. So what we can do here is we can actually sub in those two pieces of information. So the fourth term is 30. So T4 is equal to 30, which means that A times R to the power 3, because we do 4 minus 1, is equal to 30. And T6 is 480, which means that I can sub in 480. So AR to the power, so this time it's a sixth term. So 6 minus 1 is 5 is equal to 480. And here we've got two equations, equation 1, equation 2. Now what I can do here is I can start to solve for this simultaneously. Now because we're not when we're solving these simultaneous equations, because we don't have the terms adding together, we actually need to use a different operation. What I'm going to do is I'm going to divide my equations, and I'll show you why that is in the case. So here I'm going to actually do 2 divided by 1. So on my left hand side, I'm going to get AR to the power 5 over AR to the power 3 is equal to 480 over 30. And hopefully you're starting to see why I did this. Because if you have a look when I divide, this allows me to cancel out A's, and I can cancel out this as well. And I get, on my left hand side, I get left with R squared. And that's equal to, on my right hand side, I divide this, I get 16. And so therefore, R is equal to plus or minus 4. So here when we're trying to use solve to find those terms, we actually use division instead of adding and subtracting like we normally would with simultaneous equations. Okay, and then now I've done that, I'm going to sub R is equal to plus or minus 4 into, let's say we're going to sub it into the first equation. So A times plus or minus 4 cubed is equal to 30. And so therefore, yes, 30. So therefore, A is equal to 30 over plus or minus 4 cubed is 64. So that gives me plus or minus 15 over 32. So that's how we can actually figure out what these solve these problems here. We can actually work backwards just like we did in the last lesson when we sub in those specific terms, and we can use simultaneous equations to help find what a, and in this case our common ratio is. Okay, let's have a look at the next example. Example 9. A. Show that the sequence whose terms are 1,400 and 160 form a GP and find the formula for the nth term. Okay, like we looked at in the previous section, the condition for a GP is T3 over T2 is equal to T2 over T1. So let's have a look at this progression. T1 is equal to 1,000, T2 is equal to 400, and T3 is equal to 160. So all I need to do is sub these values into this formula. So let's have a look. T3 over T2. Now this time, because I'm dealing with numerical values, I'm just going to sub each left-hand side and right-hand side separately and then figure out what they are. So T3 over T2 is 160 over 400, which should give me, let me think about this, 2 over 5. And then I'm also going to check T2 over T1 is equal to, and that is 400 over 1,000, which also simplifies to 2 over 5. So therefore, T3 over T2 is equal to T2 over T1. And so that means that we've got a GP. So here we had to use that common ratio fact for proving geometric progressions. Two consecutive terms, if I divide them, if they're equal and they're equal, that means we've got a geometric progression. Now this time, oh, I forgot to mention also here, like we did last lesson, when we find this T3 divided by T2 or T2 divided by T1, that's just equal to that common ratio. So here, I'm just going to make a note here. So here, when we want to find the formula for the nth term, Tn is equal to a times r to the power n minus 1. And so here, a is just the first term. So here, our first term, T1, is 1,000. So this is 1,000 times the common ratio of 2 over 5 to the power n minus 1. And here we can actually just leave it like that and it should be fine. Yeah, there we go. Okay. So that's for part A. So part A, to prove that a sequence is a geometric progression, we need to use T3 divided by T2 is equal to T2 is divided by T1. Instead of subtracting, we're dividing this time. And once again, we can figure out what the equation for a general term in our sequence is using this formula. Okay, part B. We want to find the first term less than 1 over 1,000. So here, just like we did in the last section, we want to find Tn is less than 1 over 1,000. Now when we're solving this, and I'm actually going to move this over to the blank space over there because I want to get a bit more room, we're going to need to use a few more additional steps. It's not going to just be like a normal solving question. So actually, let's just write what we would normally have. So here, Tn is less than 1 over 1,000. I've got 1,000 times 2 over 5 to the power n minus 1 is less than 1 over 1,000. Now here we can solve this like we normally would. So let's move this 1,000 over to the other side. So I've got 2 over 5 n minus 1 is less than, well, when I move it to the other side, I divide. So here I'm going to get 1 over 1 million now. Okay, this is where it gets a little bit tricky. Notice we're trying to solve for n, and n is in my power. When we're dealing with powers, the way we can actually fix this up is by taking logs. And because when we take log of a power, remember, log of a power just means I bring down the power and leave the log there. So if I take log of both sides, so here log 2 over 5 n minus 1 is less than log 1 over 1 million. Yep. Well, this n minus 1 over here can just, using our log laws, we can just move this down to the front. So here this becomes, and maybe it's better if I just rewrote this. This just becomes n minus 1 times log 2 over 5. And that's equal to log 1 over 1 million. And so when we're solving this, I get n minus 1 is less than. Now log 1 million, I believe, let me think about this. That is just 1, 2, 3, that's 10 to the power 6, I believe. And so this just becomes negative 6 log 10 over log 2 over 5. And so n is less than 1 plus negative 6 log 10 over log 2 over 5. And so I can chuck this in my calculator, and so this becomes, and actually I'm just going to put it in the full form that we have over here. Yes, so this is going to be 1 plus log, let me put that in, negative log 1 million, 1, 2, 3, 4, 5, 6 over log, oh, let me try that again, negative log 1 million, 4, 5, 6 over log 2 over 5. Let's see what we get. And so that's 16.077. So that's 16.077. So what we're going to do is we're going to check those two values, so 16 and 17. So I'm going to go T16 is equal to T17 is equal to, now using my formula that we had here, that's going to be 1000 times 2 over 5 fifth to the power 15, and 1000 times 2 over 5 to the power 16. So let's just check this in my calculator. 1000 times, let me put a bracket around this, 2 over 5 to the power of 15. If you have a look, that's just a little bit above 1 over 1000, because 1 over 1000 is 0.001. So this is greater than 1 over 1000. And if we have a look at this guy, 16, we get a number which is less than 1 over 1000, which is less than 1 over 1000. So therefore, T17 is our first term, which is less than 1/1000. Okay, so here, when you're dealing with these questions with logs, you're going to actually, with geometric progression, most of the time you're going to be actually dealing with logs. And that makes it a little bit trickier for us for when we're solving. But still, we can still apply it in similarly, so it's not too bad. Okay, so that's how we can solve problems using with a geometric progression. I'm actually going to go through this next example on our online lesson, so we're going to actually have a bit of practice applying a few of these skills later there. But hopefully this was helpful, and I'll see you guys on our online lesson year 12. And as always, stay safe, stay healthy, stay wonderful, and I'll see you on our online lesson. Bye.